block 2. Yeah, here's our new unit. I know you don't have this slide. Now, like I said, you should have ideally already printed out the notes. You can fill in as we go along. If you'd like to take them on your own paper, that's okay too. I expect it at some points you'll probably have to pause the video so you can catch up. I'm going to go kind of quickly here, but you, as needed, of course. Wait a minute. Yeah. As needed, you stop and do what you have to. Okay? Okay, so here's kind of the crux of this unit. It's really all about this question. First of all, let me say this. We've talked about the fact that things accelerate, right? We've talked about how fast things accelerate and calculating how fast things accelerate, talking about how gravity makes things accelerate. Well, the big deal is, sometimes things accelerate, sometimes they don't. And the question is why? What makes things accelerate? Well, it has to do with the concept of forces, all right? And we can tie into that what we call Newton's laws, all right? So I don't know how long this whole topic 1 thing, topic 2 stays in there, but anyway, what's a force? Well, in the simplest case, a force is a push or a pull, all right? And since I can push this way or push that way and push in different directions, it means that force, is a vector. All right, lots of you listed force as one of the examples of vectors that you gave on your vectors and projectiles test, which is wonderful. Onward. More specifically, we say that, to be technical, a force is any interaction between objects. Anytime that objects interact with each other, they do that because they apply forces to each other. Or, through the, I don't know. But yeah, because they apply forces to each other, right? We have a metric unit of force. Pounds is the English unit of force. The metric unit is called the Newton, capital N. No coincidence that there's a guy named Isaac Newton. Hey, look, it's Shanks. Shanks wants to tell you something very helpful. He wants to tell you, I want my forces. It's a stupid way of remembering something important. You want to see that again? Yeah, Shanks. So Shanks, he doesn't say this. I don't know if he does, but I say it. The point in this side of the page, this part of the unit, is for us to be able to identify what forces act on objects. All right, and there are 5 major ones. These are the 5 that you'll have to remember. They start with a W, an A, an N, a T, or an F. All right, W stands for weight. Weight is a force. All right, and specifically it's the force of gravity that pulls objects toward the center of the earth, I wish I had said. But, gravity pulls on everything. So you weigh what you do because the earth exerts a gravitational force on you that we call your weight. Okay? A stands for applied. Applieds are always push forces. Look for push in any example to know if they're talking about an applied force. Now it says from some person or other object. Objects can't push on themselves, or if they do, we don't care about that. All right, we care about other things pushing on the object in question. All right, N's the toughest one, maybe. It's called normal. It's called a normal force. And a normal force is what I call a reaction force. All right, a lot of you have heard this idea of reaction in forces, whether or not you know it. And we say that anytime an object is in contact with the surface, whether that's a table or leaning against the wall or whatever you want, well, if the object pushes on the surface, then the reaction to that is that the surface pushes on the object. Okay? So for this, the big one is this. If an object is in contact with the surface, if that's the case, there has to be a normal force. Okay? T stands for tension. Tensions are pulls, always a pull as opposed to the push for applied. The pull from any chain or rope or cable or wire or string or blah, 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 whatever else. Anytime it's a pull. Okay? And F, everybody knows this, friction, right? I don't know why I'm not underlining anymore. Tension, friction. Friction. We all know that, well, in almost every problem we've done so far this year, we have, if not said it, we've implied it, we've neglected friction. Now we get to talk about it, all right? And the deal is anytime that an object moves or might otherwise move, friction is a force that points or that opposes that, okay? So it doesn't have to be motion. Sometimes friction can keep things from moving. But friction always points in the opposite the direction that an object is moving or would move if there wasn't friction. Okay? Okay. So those are our 5 big forces. Now, a little more about this. Oh yeah, well, this reaction force. All right. The reaction force thing is kind of comes from this statement that for every action there's an equal and opposite reaction. A lot of you have heard that. Well, that's really a statement of what we call Newton's third law, or what everyone calls Newton's third law, except it's not really about actions and reactions, it's about forces. Really, it's more accurate to say that for every force, there's an equal and opposite force. And so you'll see lots of questions on quizzes coming up and tests coming up and the Regents later on and the midterm before that. Yeah, there's a midterm. About, well, that really are Newton's third law questions. And again, they're about if one object pushes on another one, then the first object pushes back on it. And you know what I realized is we're gonna skip this page until tomorrow. Okay? Okay. Now, what do we do with this stuff? We know there are these 5 forces. What do we do with them? Well, we are gonna, in any good problem, we're gonna have to identify those forces and actually draw them. All right? So we're gonna draw what we call free body diagrams. Literally, every problem you solve for the next month is going to involve, heck, 2 months, is going to involve drawing a free body diagram, which is great, right? Because there's no excuse that you'll ever say, I didn't know how to start, because you will have drawn a free body diagram. You'll have started. That will get you points. All right? And a free body diagram is a tool. It's not just a pretty drawing. It's a tool we can use to analyze what's happening to a system, what forces are acting on a system, and what they do. Okay? A couple of assumptions. I think these are already written down for you. Don't bother drawing the elephant when the question's about an elephant. Just draw a box. And this thing says that we always assume that forces act at something called an object's center of mass. And as long as that happens, you know, if we had a ruler like this and you pushed up here, the ruler might rotate, right? We don't want to deal with rotation. We want to assume that you push right here, and that just makes the ruler slide this way. Right? We call that translational motion as opposed to rotational motion. All right, but nothing you have to really be too careful about, just something that we're assuming. All right, things like this, yeah, do your best. Yes, there are 3 rules for 3 specific forces. One of them is that weight forces, right, always point straight down. And we really mean here towards center of Earth. Okay? So weight is always straight down. Normal forces always point perpendicular, that means perpendicular, to surfaces. So whatever surface an object is on, the normal force has to point perpendicular to that. And third, friction always points parallel to surfaces. Surfaces. Okay? Okay. Just those will do you well. All right? Now let's draw some. The nice part about the first part of this unit is we don't necessarily care about solving problems. What we care about is figuring out how to draw free body diagrams. All right? And in the next couple slides, you'll see what else we have to do with that. So, but for right now, let's just start with drawing free body diagrams. All right, this is about a box being pulled across the ground. Here's the ground, here's the box. There's a rope that pulls with 20 newtons of force at an angle of 20 degrees from the horizontal. Then the question says something. Who cares right now? For right now, let's talk about what forces act on the object. So you can make yourself this checklist, right? Is there a W? Is there an A? Is there an N? Is there a T? Is there an F? Some of them can be there. They don't all have to be there. It's pretty rare that you'll see all of them. There's always going to be something. So is there a W? Does this thing weigh something? Of course it does. Weight forces always point straight down. So we got that one checked. Is there an A, applied force? Remember what an applied force is? An applied force is a push. Is this thing being pushed? Well, not that it says, so no, applied force. Normal force. Is this thing in contact with the surface? It sure is. And the normal force that the ground exerts on the box has to point up perpendicular to the ground. I call that N for normal. Check. Is there a tension force? Well, tensions are pulls. Oh, look, pulls. So yes, there is a tension force, and it pulls, notice, at a 20-degree angle from the horizontal. So I'm just going to draw it like this. I didn't use a protractor. Well, I'm going to say there's 20 degrees. Okay? Check. Is there friction? Well, it doesn't say there isn't. So then, therefore, we assume that there is. And since the ground looks like this, and the box would like to, because of that tension force, I hate to say would like to, but the box tends to move to the right, that means that friction is going to point to the left, parallel to the surface. Now, I do an F with a subscript F. A lot of people will write this tension force as Ft. Right? The only reason we don't just write F, like it's a force of habit, the only reason we don't just write F for friction is so we know we're not just, so people know we're not just saying force, general force. So I always do F, friction force, force of friction. Like we could say force of tension, for the normal force, the weight force. If you'd rather write them like that, feel free. So we're done. There's our free body diagram. We'll do stuff with that coming up, but for now, this is enough. Okay? Oh my. What in the world happened? Oh no. Oh, son of a... All right, I was supposed to put that over here, you're saying. Good, good. Weight, tension, normal, friction. Okay, next is a sign is hung from two cables. Yep, okay, here's a sign hung from two cables. One of them goes at 50. We'll do this one's at, 50. There's 50. And the other one's at 40. That one's at 40. Sure. Oh, I'm not going through the checklist. I guess I should do that. I know it's hanging from. So is there weight? Of course it weighs something. There's its weight. Check. Is it being pushed? Nope. Is it in contact with a surface? Nope. Is it being pulled on? Yep. We're going to do this. T1, T2. Two different tensions. Check. Friction. Well, it's hanging in midair, right? And ideally, signs just want to hang there. And the other thing is this. In order for there to be a friction, this sign would have to be dragging across the ground or rubbing against the wall or something like that. So no friction. That's it. There's your free body diagram. All right? Do it. Now, we want it when she's cruising along the hill. No, not the hill. No. We want it when she's down here. So she's coming down the hill. Now she's cruising along this way. Here she is. Draw me a free body diagram for the girl on the girl in the sled. That's kind of the system. We call that the system. The girl sled system. Not the girl, not the sled, the whole shebang. Okay? Draw me that free body diagram. Next! Now, what was topic 2? I don't know. What was oh yeah, free body diagrams. Topic 3, net force. And now that we're professionals with this free body diagram stuff, what we have to do is we're going to This will be the next step in every problem you solve. You will draw a free body diagram, and you will write what we call net force statements. You know what net means? All you working people, you get a paycheck, and you get your gross pay, and you get your net pay. You know what net means? Net means, oh, it means total. Total. So the net force acting on an object is the total of all the forces, or the sum of all the forces acting on an object, or the resultant of all the forces that act on an object. There can be simple cases like this. Let's say we have two forces like yay. We got a 20 Newton force this way, and also a 10 Newton force this way. Oh, you know what the net force is? I bet you do. Wait, where is it? Oh, it's over there. Well, no, the net force, of course, is 30 newtons. Which, oddly enough, you get if you added these tip to tail, right? If we move this 10 over here, tip to tail, oh yeah, there's 30. If they point in opposite directions, we can get something like this. Let's take that same 10 newtons, and we'll take this. We'll take this 20 newtons like this. Net force, anyone? Anyone? Very good. 10 newtons upward. Notice our resultant force, our net force, our total force, has a magnitude and a direction. Yeah, what if we have like this? I don't know, let's change this now and say that these are both like 15 Newton forces. Well, if they're in opposite directions like this and they're of equal magnitudes, you know what the net force is? We say the net force, we do it like this. The sum of all forces, the net force, is 0. Does it mean there are no forces acting on an object? No, it doesn't. It means that the forces add up to nothing. So it says net force is 0, right? Net force is 0. Exclamation point. Good? Good. Now a little more, what's the word? Complicated? I don't know. A little more realistic, I guess. We might have forces that are not what we call collinear. They're not all, either this way or this way or this way. Sometimes, in lots of cases, well, like we saw in some of the free body diagrams we drew, we get forces that are perpendicular. Well, there are no forces that are called B, right? There's W, A, N, T, F. I'm just using very general. Here's a, I don't know, some force I'm just calling B. Who cares what kind of force it's supposed to be? Some force I'm calling A. Who cares what kind of force it's supposed to be? Well, wow. We're going to treat these a lot like we treated projectile problems, right? In projectile problems, what we did was say, well, here's a projectile, and at this instant, it's moving this way, and it's moving this way. Well, the only force on it is that way from gravity. So, yeah, sure, let's talk about this direction because gravity works in that direction. And sure, let's talk about this direction because gravity has no effect whatsoever on that direction because they're perpendicular. All right, we're going to do the same sort of thing in this unit and look at the net force in the horizontal direction and the net force in the vertical direction. All right, again, this is how you'll start every problem. You'll do a free body diagram, and you'll write these net force statements. All right, and forces that act in the horizontal direction have nothing at all to do with forces that act in the vertical direction. All right, so it's important that we're able to separate those things that happen in different directions. Just like it was really important when we did what do you call it? Projectiles. Thank you very much. So when we do this, net force in the x direction. Well, what we do is literally, x means side to side. We look for any vectors that point side to side. Well, right now, all of them is A. That's it. All of the ones that point in the vertical direction, y for us means up and down, is B. Okay? Let's say there was this force C, that points downward. Well, notice that has nothing to do with this stuff. It's not a horizontal force, it's an up and down force. So it goes over here. Except B points up and C points down. So what we do is we do this. Really, we're saying this. B points up, it's positive. C points down, it's negative. Right? You've seen this before in math. This means add them all up. Right? Well, we are adding this one, but we're adding it negatively because it points downward. Right? So we call the net force B minus C. Oh, snap, look at this one. We have force D. Well, that's not in the side to side or the up and down direction. So where do we add it? Well, you can't put D anywhere, but what you can do is break D into components and put the dx component here and the dy component there. All right, now, dx points to the left, A points to the right. So really, let's do this. Right's positive, left is negative. By points up just like B does. Let's make that positive. What do you think? Now, like I said, we're not going to have free body diagrams with A's and B's and C's and D's. We're going to have ours with W's and A's and N's and T's and F's. But as long as you can, as long as this makes sense to you that you can split forces into directions and look at only horizontal stuff together, only up and down stuff together, right? That's a real important part of this unit. All right, so let's do a few. We'll do 3. Oh, what? Okay. Yeah, all right, so we have the same ones. Good. We have the same ones from before. It's time saver. That's what I'm talking about. So let's do this. T, W, force of friction, N. If you're saying, wait a minute, how'd you know that? It's because we did the same example a couple of slides ago. Remember? Good. Now, here's a great thing to do. Right away, we see a force at an angle. Let's break it into Tx and Ty components. All right, I'm going to put theta right there. Yeah, it's 20 degrees. I'm just going to write theta. Okay, let's do a net force in the x direction. Well, I see, again, that means this way, back and forth this way. I see Tx minus force of friction. That's all I see. Right? Really, if you want to write it like this, Tx is positive, it points right. Friction's negative, it points left. That works just fine. That's all we have. Now, in the vertical direction, we have this. That means, again, y is up and down. Notice we have n pointing up. We have w pointing down. A lot of people will stop there and miss the fact that there is this one pointing upward, plus Ty. Well, what do you think? Okay? It's all right? It's all right. All right, next. Let's go back to our hanging sign here. It weighs W. I think we did this before. T1, T2. Like I said, when you see forces that pull or push at angles, you should immediately T1x, T1y, break them up into components. T2x, T2y. Weight points straight up and down. We don't have to break that up into components. It's all y stuff. It doesn't have an x component. Yeah. Okay, net force in the x direction. Well, it looks like this. Again, all stuff going this way and this way. Well, T2x points in the positive direction. T1x points in the negative direction. Yeah? Good? Good. Y direction stuff is all up and down. The up stuff, I like to do the up stuff first. So I see T1y pointing up, I'll make it positive. I see T2y pointing up, we'll make it positive. I see W pointing down, I'll make it negative. Okay? Ooh, I'm going to go to the next phase. It's nothing new. The question is, how are we going to find Tx? Well, notice, like if you know what T is and you know what the angle is, remember that from projectiles? You better. How do you find the components of any old vector A? Remember that? Here's AX, here's AY. Well, AX, so says your reference table, is A times the cosine of theta. AY is A times the sine of theta. So I'm going to go one step farther and say that Tx is T cosine theta. You can leave that positive there if you want, or get rid of it. Over here, I'm going to say, well, that's still just N minus W plus Ty is T sine theta. All right? Like I said, this stuff, being able to deal with the components stuff, just has to become sort of second nature to you. It has to. All right? If you have to stop and think about it a little bit, fine. But the quicker you can come up with, oh, here's how I go from component to, finding the component, the better off you are. So T2x, well, we'd have to do this. We have to call this like theta 1 and call that theta 2. So we can say that T2x is T2 cosine theta 2. And T1x is T1 cosine theta 1. I gotta hurry. The bell. T1y, T1 sine theta 1. T2y, T2 sine theta 2 minus W. Okay? Now your job, is you're going to have this free body diagram. Again, not when she's coming down the hill, but when she's on the ground. And then I want you to write the net force statements. So you will have this box filled in, and this box filled in. Yeah. Good? Okay. Adios. What's up, Barbara?